presentation, and we should move on to our next speaker. We have the paper Simple and Memory Efficient Signature Generation of XMSSMT by Haruhisa Kosuge and Hidema Tanaka, and I think Haruhisa will give the talk. I cannot hear because you're muted.
Thank you for the introduction. Our work is to improve the signature generation algorithm for XMS-MT. XMS and XMS-MT are hash-based signature schemes which only use hash functions and box cipher. As you know, hash-based signature schemes are believed to be secure against large-scale quantum computers in the future. And XMSS and then XMS-MT have already been specified in IFC and NIST-SP 800 series. In short, XMSS is a Markov hash tree in which each leaf is used for one-time signature. And XMS-MT is a layered XMSS. It has multiple trees like this. If this scheme is naively implemented, the signature generation requires an exponential time with respect to the height of trees. Fortunately, there is an algorithm called the BDS algorithm, which can generate signatures in the linear time complexity. The BDS algorithm is applied to XMSS without further consideration, but it cannot be directly applied to XMS-MT, and there are things that we should consider. So we choose this as our target. In 2013, Housen, Rausch, and Bahama proposed the algorithm for XMS-MT using the BDS algorithm. This existing algorithm is a truly good algorithm, but there are two disadvantages. First, the state size is large. Sets should be stored in rewritable non-volatile memory, such as flash memory. In some implementations, such as in smart cards, such memory is scarce and easy to wear out if the memory usage is high. And so it is important to reduce the state size considering such implementation. Second, the procedures and the state structures are complex. From the property of XMSS and XMS-MT, they are vulnerable to implementation bugs. The security of schemes is based on assumption that one-time signature generates only one signature. It sounds very easy, but XMS-MT managed to prevent such multiple signature generation using the state. If a minor mistake in state management leads to the security collapse. So the procedures and the state structure should be simple to prevent the implementation tags. For these motivations, we propose a new signature generation algorithm for XMS-MT, which overcomes the disadvantages of the existing algorithm. And first, our algorithm retains almost half state size. And second, our algorithm has simpler procedures and simpler state structure. And also, we implemented our algorithm based on the reference implementation of RFC A391. That's all. Thank you for listening.
Okay, thank you very much. Don't forget to write your questions in the chat, and we will move on to our next talk. Zaytun, I hope that's how I should pronounce it. Zaytun, lattice-based PKA and CAM with short ciphertext size by Farhad Abla and Mingsheng Wang, and I think Farhad will give the talk.
Yes. So now I can't share.
So
Can share my screen.
you cannot share. Then Haruhi-san should stop sharing his screen. Okay, so try now.
No. It's okay now.
Yeah, seems to work.
Oh, okay. This talk is about a lattice-based PKE and CAM with shorter ciphertext size, and I'm Farhad Abla. And this talk is why we choose lattice, because lattice is simple and efficient, and we have a worst case to average case reductions, and we can also construct many other cryptographic schemes. And this talk, we construct a PKE and a CAM based on the ring LW assumption. And another assumption, we call this a intro assumption, which is simply different from the intro assumption. We just add a Q over 2 to the second term E. Previously, there's a ring LW based PKEs. The PKE, the KJ algorithm generates a PK. It consists of 2 ring elements. In the intro-based PKE, there's 1 ring element. And in encryption, there's 2 ciphertexts. And intro-based PKE, there's 1 ring elements. But we observed that in the NIST PQC standardization competition finalists, there's a LW-based schemes and intro-based schemes, but the public keys and ciphertext are almost the same. But we think that why there's a intro-based schemes have consist of 1 ring elements, and finally they come up with the same ciphertext size with the lattice-based ring LW-based encryptions. So reason is that in the intro-based encryption schemes, we can't compress the ciphertext, because compressing the ciphertext will swap the message mu. But in the ring LW-based encryption, we can compress the ciphertext. If we compress the ciphertext and decompress, we will add small errors to the final error, and we can still decrypt the ciphertext. So our motivation is to can we alter the intro-based encryption, and we can still able to compress the ciphertext. So we tried two naive tries, and we just generate a LW-based Cajun algorithm and plus the intro-based encryption, but still failed to decrypt them. And we tried intro-based Cajun and LW-based encryption, we still failed to decrypt them. So in our paper, we construct another encryption, and we call them Dayton. And the encryption, the public key is very similar to the intro-based encryptions, just 1 ring element, and we just add a Q over 2 here. And encryption is 1 ring LW samples. So we can compress this C, the ciphertext, and decompress the ciphertext will add some error to there. The decryption is very similar to ring LW-based encryptions. So here we used another technique that this 2 term, the multiplication of this 2 term will concealed by modulo Q, almost concealed by modulo Q, so we can still able to decrypt the ciphertext. And we construct a CAM. For the CAM, we didn't encrypt the random message. We just encrypt the lower bits of the random element R here. So our CAM scheme is very efficient and very shares a very small ciphertext size. We give a reference parameterization here, and we can compress the ciphertext. If the ciphertext is 1 ring element and every coefficient consists of 0 to Q. If Q is almost 12 bits or 13 bits, and after compressing the ciphertext, we will only left 4 bits. And we compress our encryption with the NIST third round submissions. Our ciphertext is almost 256 bits, bytes. Previous schemes have almost 800 bytes. So we can save many space here. And that's all. Thank you.
Okay, thank you very much. And we move to our last talk, a polynomial time key recovery attack on the Sidon crypto system by Pierre Buyot, Javier Verbel, and Jean-Pierre Tilly. And Pierre will give the talk.
Yeah, I'll try to share my screen. Is it fine? Do you see my screen?
Yeah, seems to be working.
Okay. So in this paper, we propose an attack on the Ceton crypto system, which was presented at PKC this year. So the Ceton crypto system is a multivariate scheme which relies on the theory of Ceton spaces. So Ceton space is a subspace V of some extension field FQN of dimension K, such that if you have 2 pairs of elements in V which have the same product, then these 2 pairs are identical up to a multiplicative factor in FQ. So concretely, this means that you have unique factorization. If you start with a product AB which lies in the product space V times V, then this element corresponds to a unique pair AB up to a multiplicative factor, because you can still replace this pair AB as any pair of the form A times X B over F if you take X which is non-zero in FQ. So there are many subspaces of FQN meet this property, but for the scheme, we need very specific ones. Because the idea of the scheme is that the plain text is a pair of elements in V, and the ciphertext is a product of these 2 elements. So to construct the scheme, we'll need a Sidon space V which admits an efficient factoring algorithm A. And in particular, the secret key is the parameters of this algorithm. So first, a basis nu for the V and a basis beta for the extension field. And on the contrary, if you want to encrypt, you must be able to perform products in V without knowing the structure. So for this, we're going to reveal a multiplication table, which is a set of n matrices M1 to Mn, which satisfy this equality. So you can obtain these matrices Mi's from the secret matrix mu, which is simply nu, the transpose of nu times nu. So then to encrypt your message here, you simply have to compute some matrix vector products with your public key. And your ciphertext is a vector of length n over the base field FQ. Then to decrypt your ciphertext, you first simply map it to the extension field by using your basis beta. And then you remark that this ciphertext actually is a product of elements in V, and then you can use your secret key to recover the plain text. So really for cryptanalysis, the fundamental identity is this one, because the attacker wants to retrieve the secret key from the public key can solve a min-rank instance. So the min-rank problem is a famous problem from multivariate cryptography. And here the goal is starting from your n public matrices MIs. Your goal is to find a low weight linear combination between these matrices, and here the weight or the rank is equal to only 1. So it's quite particular compared to regular min-rank instances. It is a min-rank instance with rank only 1. So why is this relevant here? Because the secret matrix MNU from before, if you use your identity, it is a solution to this problem with xi equal beta I. So in fact, to assess the difficulty, to assess the security of the scheme, we have to evaluate if this instance is difficult to solve. So first, how many solutions are there? Is it difficult to recover them? Another source of hardness comes from the fact that even if this instance is easy to solve, it's actually hard to extract the secret matrix MNU or any other relevant matrix to perform a key recovery. So now, the Sidon crypto system uses a very specific construction for the Sidon space V. And what we show in this paper is that if you use this very same construction, in fact, the key recovery attack by solving the previous min rank instance is in fact really easy. This is because first we are able to show that this min rank instance has many solutions, and in fact, due to the structure of the Sidon space V, this solution belongs to a subfield. And also we show that from these particular solutions, it's very easy to recover an equivalent key. So this is not directly the matrix MNU, but this is a matrix which allows to decrypt any ciphertext. So this really breaks the schemes because both steps are polytime. But the good news is that it doesn't mean that the whole idea to use Sidon spaces for crypto is bad, because you can still repair the scheme if you use another construction for the Sidon space V. The only drawback is that few explicit constructions of this type exist, and they are essentially all summarized in this paper. So for the moment, there is no direct way to repair the scheme. So thank you for your attention, and don't hesitate if you have questions.
Okay, thank you very much. And we have around 10 more minutes, 15 minutes to answer questions, but I don't see any questions in the chat, so please don't be shy and ask our speakers what interests you. Perhaps in the meantime, I can ask my first question. I have a question for Ward. So you say that you have an ad hoc construction of this whipping procedure. Mm-hmm. Yeah, and we need to read the paper to see what it is. But could you please tell us what the hardness of this problem is, or to which problem you relate the hardness of your construction?
So the assumption is that if you somehow take the smaller map and whip it up into a larger map, then the large map is still preimage resistant, and basically there's no reduction, like there's no good reason why this should be difficult, except for the fact that I couldn't find any attacks. So really that's all that there is to it.
Okay, and what would be the best attack to give some intuition of?
So right now, the best attack I know is just you forget the structure, you don't know that it's whipped up, and you just attack it like a random system.
Oh, like a random MQ system.
Yeah.
Okay. Thanks. We have some questions. Thanks a lot. We have some questions for Zaidun. What can you say about the security of your scheme, asked Andy Helsing?
For the INT-CPA security, we need a ring LW assumption and the INT assumption, both of two assumptions. For one-way security, we just use INT security. INT assumption is enough.
So you do have a security proof?
Yeah, in the paper we give the proof. We just give the IND CPA security proof, and we just that's implied. One-way security is implied by INJ assumption.
Okay, and I have a question also for Parhat. Is there? Could you tune the parameters differently and get different decryption failures? Is that possible?
You mean?
So you kind of like, from what I understood in your construction, you introduce a bit of error, and this increases the amount, the possibility of failure. Yeah, is this tunable?
Yeah, it's tunable. Because we can compress the ciphertext and the public key. A public key is compressible in intro encryptions. So if we compress the ciphertext, the decryption failure will decrease. The previous intro-based encryption schemes are 2 to the 20 to 100, and in our scheme it will fail to the 121.
Okay, thank you. We have another question for Pierre. Is the CDON scheme broken for all instances based on min rank where the minimal rank is 1? Asks Krijn Reinders.
In fact, by definition of the scheme, you can always attack it by solving a min rank instance of rank 1. They have proposed several ways to try to have a higher rank min rank instance, but they have not proposed like the scheme to build it. So for the moment, the only way, I mean, there is no like equivalent of a CDON crypto system where you would have to solve a higher rank min rank instance.
And is this related to what you said that having a better structure of V, you can save the scheme? So do you mean by better structure that you don't have a min rank instance of rank 1? Or
the thing is that for the moment, all the structures of CDON spaces for which we know a factoring algorithm, at least the one I gave in the paper, they rely on an intermediary extension field between FQ and FQN, and this is what makes the weakness of the min rank instance. So in fact, this is a min rank instance of rank 1, but also there are a lot of weakness due to the intermediary extension field.
Oh, okay, okay. I see. Okay, thank you. And Keita Harava, sorry, I can't pronounce that, to Parhat Abla, your proof seems to have a problem similar to the original Kyber Sabre since your H is compressed. Why can we use RWE? RLWE.
Why we can use in the proof? You can see that in the scheme, if we use ring RW assumption, we can just simply replace this C, the ciphertext, with a random element. So it's independent of our message here. So that's why we use the ring RW assumption. If you don't use the ring RW assumption, that's okay, and you just assume that this kind of ciphertext is a one-way encryption. That's well defined. And I didn't understand why the Kyber. The question is.
Yeah, please, maybe Keita wants to explain a bit.
Sorry, excuse me, so can I speak?
Yes, of course.
So you omit So in this case, so you omit the compression and decompression.
Yes. Yes.
And so you first replace H with random one
Yeah.
by using inhomogeneous N2 assumption.
Yeah.
Then
After
so
that-
you so after that, so what the problem is that so you have compressed H. So therefore the C is H times 2R plus mu plus E prime, and
And plus
H
NL.
is decompressed one.
Yes.
So is it the
The compression and decompression is publicly known. So
yeah.
so that didn't interfere with the proof.
Really? Yeah, I think
It's just it affects the decryption failure, but the proof is the same.
Okay. Thank you. So, thank you.
Thank you.
Okay, maybe this is something to take.
Yeah, we can talk about that offline.
Yeah.
Are you?
Offline. Maybe.
You can anytime.
Yeah.
You can contact me. I have an
thank you.
email.
Yeah, we have
I-
some
I
social
ask
events
you-
later on.
Yeah.
Thank you.
Okay. Good. Thank you. Any further questions? I have one more question for Haruki-san about the construction of the signature. Does this algorithm in any way impact the security of the scheme, or is it purely an implementation thing?
Yeah, it's truly about implementation because the format of the secret keys and the public keys and signatures are the same. So if we don't consider the certain channel attack, the security is the same. Doesn't impact the implementation doesn't impact the security at all.
Right, and for side channel attacks, or you didn't talk
I
about this
didn't.
in the paper?
Yes, yeah, it left there the open problem.
Okay, that's definitely interesting.
Yeah.
Oh, okay. I want to thank everybody. Our time is up, and we should continue with the next session, I think. And Peter?
Hi, I'm Peter Kutash, and so the next talk, or the first talk of the second session, is by Andrei Schrottenloher, and it's improved quantum algorithms for the K-XOR problem. And I suppose Andrei is going to give the talk.
I think you should be able to see my screen.
Hmm?
You should be able to see my screen, right?
Yeah.
Perfect. Thanks for the introduction. So yeah, this paper is about quantum algorithms for the K-XOR problem. So what is it? First of all, we basically have two flavors of this problem. The one where we're going to have many solutions, and the one we're going to have a single solution. The many solutions, so basically we have access to let's say a random function, something that produces some data, some bit strings, and we want to find k inputs whose image is XOR to 0. And of course, in some cases we can have many data, so we have many solutions for this problem. In some cases we can restrict, for example, the domain of this function so that there is a single solution on average. Now I'm taking the XOR operation just because everything is very simple when you think of it, but all these algorithms also work with modular additions, for example. So this problem is like a prototype of some hard problems that you'll see often appear. You can, for example, you can reduce subsets into that. And it's a problem that is also like, there's going to be difficult for quantum computers. And in particular, we're going to expect basically square root quantum speedups at best. And usually it's going to be less. Also, what's very important is that the query complexity and the time complexity are very different. So we're going to focus on the time complexity here. Basically, we want to use this as a black box, as a tool for cryptanalysis. Okay, the query complexity is always 2 to the n over k, because if you take 2 to the n over k elements, you can just take all the tuples you can make with that, and one of them is going to go to 0 with high probability. The time complexity in the many solution case classically is given by an algorithm by Wagner. So the time complexity exponent is depends on log2 of k. There is a formula for that. And in the single solution case, the classical setting, it's basically always 2 to the n over 2 roughly. Now, there has been now previous work on the quantum time complexity, and the best were obtained in a paper we did with Marina Peasantsia at Europe 20. And there is something that looks a bit like Wagner's algorithm in the many solution case. And in a single solution case, you get an exponent that depends on k, and it basically reaches a minimum 0.3 in some cases. So this paper started with the goal of basically representing the same class of algorithms in an easier way. Because in the European paper, you find a definition of these quantum algorithms as based on the definition of certain trees, merging trees, which is maybe not completely natural. In particular, it differs from the classical definition, the definition of trees we use for classical algorithms, basically. And okay, so in this paper, what we did was introducing a new definition, making things a bit simpler, and also like the analysis of the algorithms. Turns out that, well, this is still going to be the same class of algorithms in the many solution case. Now, in the single solution case, there are some constraints, like especially one that can be modified, and you can get better complexity from that. And so this best exponent in the single solution case goes from 0.3 to 2 over 7, just a little below. And there are some other improvements. Basically, if you're interested in a 4 XOR instance, the time complexity could be reduced to 2 to the 7n over 24, many fractions. So since I have like 1 or 2 minutes left, I'm going to explain this 4 XOR example very briefly. It's actually a very simple algorithm, a bit deceptively simple. What you do in the classical setting for this is you start from this 2 to the n over 4 data, and you want to find, right, you want to find this tuple that goes to 0. So what we're going to do is we're going to choose an arbitrary prefix of n over 4 bits. And something that is really easy to do is from 2 lists, we're taking all the sums of elements which have this prefix s. So we can do that in time to the n over 4. We can just go through the list, find all the sums. This is a merging operation. And once we have done that, we can check if there is a collision between these lists. Most of the time, there is no collision. But for a single good value of the prefix s, on average, there is going to be one. And this is going to be our 4 XOR instance. Well, this is an algorithm that in total has 2 to the n over 2 time complexity, as expected, and 2 to the n over 4 memory complexity. This is Chopin and Chamiè's algorithm. In the quantum setting now, things become a bit different. But this is still the same tree, which is basically the emphasis of this paper. We start from our list here and assume that we have fixed this value s. Now what we want to solve is a problem that is finding a collision, if there is one, between these 2 lists that I put in green. And we can use a black box quantum algorithm to solve that. There are actually efficient quantum algorithms to solve that, especially running in time the size of the list to the n over 4 power 2/3. And you can see really this problem, this 4 XOR problem, as a merging problem between these 2 lists, green lists, as soon as you're able to basically sample the elements of this list efficiently, which you can do. So basically, in the end, you have a quantum search, well, a search of the good value of S, but in the quantum settings, so we get a square root factor on that. And you have this collision color finding problem to solve. And this is where you get a complexity, which turns out to be a little below the previous base complexity for Photo. But this is only an example. Well, there is a generic definition. There are generic definitions in the paper and also generic formulae that I didn't put in these slides. So yeah, so in this work, you find a simplified representation and hopefully a simplified analysis of these algorithms and some improvements in the single solution case. And as I showed in the Folkzo example, there is also the possibility to combine with so dedicated color finding algorithms, so basically quantum root algorithms. I don't know if the combinations can be done further. It's a bit unclear, and it's also a bit unclear if that can help to improve the lower bound 2/7 on the exponent, but it's an interesting open question. So you find the full version of this paper on the prints, and I thank you for your attention.
Thank you. So the next talk is by Wolf Frickson, Maria Naya Plasencia, and Andre Schottenloher about quantum boomerang attacks and some applications. And Paul is giving the talk. So please share your screen.
Okay. Thanks for the introduction, and I will present our work on quantum boomerang attack and some applications. So I will talk about boomerangs and how to make the boomerang distinguisher into key recovery attacks. Then a word about the quantum versions of those attacks and some applications. So what are boomerangs? So we start with two high probability differentials on half of the block cipher. Then we start with a pair of plain text with difference alpha, and we get a difference beta in the middle of the block cipher. Then with the ciphertext, we get two other ciphertext, and such as we get two other differences in the middle of the block cipher. Then the three of them, we get a fourth one, and then we get back a difference alpha between the returning pair P3 and P4. So it makes the basic boomerang distinguisher, taking P1 at random, building the rest, and checking if we get the good difference. So this distinguisher succeeds with probability PQ squared because we use each differential twice. Then how to make key recovery attacks. So we will use an additional run on the block cipher. Then on this additional run, we will define the set of obtainable differences from delta through that additional run, and pay out the probability of getting delta back from an element of the phi. And we will also assume the additional run to only involve a subkey. So here is the new situation, and the last round attack will imply three steps. The first one will be getting this event to happen, then recovering the subkey on the last round, and guessing the rest. Then we made quantum equivalence of those two attacks, and on each of them we made a quantum version that succeeds with a near quadratic speedup of the classical version. And there are more details in the. So we made applications. The first one being on a 5-run Cepher plus. And there is a classical boomerang with a time complexity of 2 to the 78. And we made a quantum equivalent with a time complexity of 2 to the 53.6. Then we made a another application on AES in the related key model. So there is a classical boomerang with time complexity of 2D99.5, and with our framework, we made a quantum equivalent with the time complexity of 2D96.4. So to conclude, we propose the first efficient quantum boomerang attacks with, in theory, near quadratic speedup, and we apply those on the related key AES and CipherPlus. And the quantum speedup highly depends on how the attacks are made in practice. This is when there were difference between our results on application and it is quite far from the near quadratic speedup. So thanks for listening.
Okay, thank you. So the next talk is by Jorge Chavez Saab, Francisco Rodriguez Henriquez, and Mehdi Tibushi, and it's called Verifiable Isogeny Walks Towards an Isogeny-Based Post-Quantum VDF. And Jorge is going to give the talk. So the floor is yours.
Yes, hello, thank you for the introduction. So I'm going to talk about verifiable isogeny walks and how we can use this to get post-quantum verifiable delay function. So let me first talk about what is a VDF. Verifiable delay function, basically, the idea is that we have a function whose output is determined at the moment we pick an input, but no one is going to be able to guess what it is or to compute it before a prescribed delay, which we call capital T. So formally, it consists of 3 algorithms that are the setup, eval, and verify. And the most characteristic property is that of sequentiality, which is that no algorithm should be able to replicate the output of eval in time less than t. And here it should be noted, we are referring to wall clock time. So to begin with, we expect it to be a highly sequential function, such that it cannot be sped up, even if you have an amount of parallelism that is polynomial in t. But then you also want it to have efficient verification. So once someone has computed the output, everyone else should be able to verify it faster than t. And VDFs actually turn out to be very interesting primitives. They have a lot of applications, including public lotteries, randomness beacons, verifiable benchmarking, proofs of storage, and power efficient blockchains. So what we propose is that we can build a VDF that where the evaluator must compute a chain of isogenies between elliptic curves. So what I have represented here in this graph, each vertex is a different isomorphism class of elliptic curves, which are represented by a special quantity called the J invariant, and the lines between them are isogenies. So there's a lot of math behind isogenies and elliptic curves, but for this, really all you need to know is that there's a special polynomial called the ELP modular polynomial, where 2 elliptic curves have an isogeny of degree L connecting them, if and only if their J invariants are roots of this polynomial. And this polynomial is of degree L plus 1. So the method that we propose is that the evaluator just computes the next J invariant in the walk by finding roots of this polynomial. And a nice little trick that we use, we only use isogenies of degree 2, so the modular polynomial is of degree 3. However, we always know one of the roots because we're doing a walk, so the previous vertex in the walk is always going to be a root because isogenies are symmetric. So we can exploit that and just factor out that known roots, and we reduce it to a quadratic polynomial. And then, so the other 2 roots explicitly are given by these equations down here, which just comes down to taking a square root of a discriminant and choosing a sign, right? So in this sense, the walk is uniquely determined by a sequence of choices of signs. So this sequence of signs is what we're going to obtain directly from the VDF input. And now the equations that you just saw for both the discriminant and the next J invariant itself, they're just an iterative procedure. So for the verification, we propose that it can be verified by a SNARK, which is short for succinct non-interactive arguments. And these are just general procedures that can be used to verify any computation, quote unquote, efficiently. Although here efficiently just means in terms of the complexities. In terms of concrete cost, they're usually deemed theoretical because even like the state-of-the-art implementations introduced a lot of overhead, which is factors of about 100,000. However, we argue that this is only for, well, this is the case for very generic SNARKs, whereas we can save in overhead by specializing to our case and building a SNARK over the field of the elliptic curve. So like a universal kind of SNARK would, for example, keep track of all the register values in your CPU for any given program, and then verify each of the ALU operations. Whereas what we propose is just a SNARK which keeps track of field elements only and verifies the steps of field arithmetic. So basically the insight is we know the verifier is able to do field arithmetic himself, so it's not really necessary to build a proof at that level of detail. And we expect that this could potentially save a lot of overhead, although admittedly, exactly how much we don't know because we haven't benchmarked this. So these are the theoretical results that we got. We were able to get an evaluator of order T as long as he has access to polylogarithmic parallelism and linear space in T. And the verifier runs in time that is quasi-polylogarithmic in T. And also we claim that this construction is post-quantum, which is actually the first instance of a post-quantum BDF based on isogenies. And even if it may still be theoretical, but because of the inefficiency of SNARKs, we think it's still a very interesting result because it has all the right complexities for a BDF. And for future work, we still want to implement and benchmark this to just figure out exactly how theoretical it is. And then this should help us propose concrete parameters in terms of the desired delay. And that would be all. Thank you.
Thank you for the nice talk. So the next talk, I messed up the schedule a little bit. So the next talk is the paper by Sabrina Kunzweiler, Jan Botti, and Charlotte Weidkemper, Secret Keys in Genus 2 SIDH, and Charlotte is going to give the talk. So the floor is yours.
Can you see my slides?
Yes, we can see your slides.
Right. So thanks for the introduction, Peter. And I will continue talking about isogenies with the genus 2 variant of SIDH, and specifically the key space and how to recover a static key. And this is joint work with Sabrina Kunzweiler and Jan Botti. So just to give some quick introduction, SIDH is the supersingular isogeny Diffie-Hellman protocol, and it's a key exchange scheme by Zhao and DeFeo, and it uses isogenies of supersingular elliptic curves and some additional torsion point information to make the diagram commute in order for Alice and Bob to derive a shared secret in the end. The genus 2 variant of this is a higher dimensional generalization introduced by Flynn and T, and it uses principally polarized superspecial abelian surfaces instead of elliptic curves. And Alice and Bob use 2-2 isogenies instead of 2 isogenies and 3-3 isogenies instead of 3 isogenies, like in the SIDH case. And these sequences of isogenies are determined by some secret scalars. And in order to make the whole protocol work, we need to only consider isogenies of a certain type. And these are the isogenies which have a maximal isotropic subgroup as a kernel. And this roughly means that there are some Weyl pairing restrictions on the subgroup. So we need the Weyl pairing between any points in these subgroups to be trivial, and the subgroup to be the maximal subgroup in the torsion group with this property. And if we use these types of kernels for our isogenies, we can preserve the principal polarization of the abelian surfaces. And it also means we have rank 2 or rank 3 kernels rather than cyclic kernels like in SIDH. So basically Alice's subgroup is determined by these secret scalars. And these 12 secret scalars determine the 3 kernel generators of her secret subgroup. And due to the extra conditions on the Weyl pairing, the key generation is quite involved. We have to solve some linear congruences so that the Weyl pairing is actually trivial on these points. And the issue is that the original strategy that was proposed for the protocol does not always determine a valid subgroup. And we also don't know how to uniformly sample from the key space. And to tackle these issues, we suggest the use of a symplectic basis for the 2 to the n and 3 to the m torsions. And this means that the basis points satisfy some Weyl pairing values between one another. In particular, we only have 2 pairings which are a primitive 2 to the nth root rather than 1, which is the value all the other pairings give. And using a basis like this has the nice advantages that we don't need to check as many conditions during the key generation because some of the pairings are already trivial. And also the symplectic property of the basis is not affected if we apply or if we evaluate the isogenies that we use in the scheme. And we also find a way to classify all the maximal 2 to the n isotropic subgroups. So when we write these scalars defining a subgroup in some sort of coefficient matrix, we can use a strategy that is similar to Gaussian elimination to obtain normalized forms of the matrix so that we have normalized kernel generators. And it's possible that we have to, during this strategy or this elimination process, that we have to permute some of the columns, but this doesn't affect the subgroup in the end. And if we fix some rules for applying these column permutations, we can uniquely identify each subgroup G with 4 scalars A, B, C, D, an integer K, which defines the structure of the subgroup, and the permutation sigma, which indicates the permutation of the columns. And then we can look at the original key space, which contains all the L to the n isotropic subgroups of the L to the n torsion. And in particular, all different types of subgroups that we have determined in our classification process. But it's really hard to sample from this key space. So we introduce a restricted key space, which looks at only the rank 2 kernels where the columns don't need to be permuted in order to find the normalized form. And this means that we can identify any element of the restricted key space with A, B, and C scalars, which are all integers modulo 2 to n. And what is nice here is that the sizes of these 2 different types of, or these 2 key spaces have same order of magnitude, so we don't lose out on much security. And this is too dissimilar to what is common in SIDH at the moment, where we only consider secrets defined by a single scalar rather than 2, like in the original proposal. Our second goal was to find an active attack on the scheme, which recovers any type of kernel that Alice uses when the adversary impersonates Bob. And for SIDH and certain variants of SIDH, there's an iterative strategy proposed by Galbraith and al., which is called the GPST attack, and it sends malformed torsion points and then iteratively makes deductions about the key bits from the information that is returned from the oracle that models the attack. And this response from the oracle indicates whether the malformed Trojan point information leads Alice to compute a different variety in the end from the one that would have resulted from an honest protocol run. The problem here is that in Genus2S-IDH, we don't have cyclic kernels. So basically, we need to be much more careful when we generate these malformed points in order to feed the oracle with a valid input. But we managed to do so with using symplectic transformations to find the correct malformed points. And these evade all the common simple countermeasures. And these are whether the points are of correct order or whether they satisfy the Weil pairing conditions or form a symplectic basis still. And in the end, we end up with an algorithm on how to determine the type of subgroup that is used. And we also find a way to find the normalized representatives corresponding to both rank 2 and rank 3 kernels. Yeah, I think I'm probably over time already.
I think you're running out of time, so if you just
yeah.
Maybe.
Basically, what we do in summary is we look at Genus2S-IDH where we use symplectic bases, and this means we can enumerate all the possible kernel subgroups, and we can also find an adaptive attack. Sorry for running over.
Okay, no problem. Okay, thank you for the nice talk. And then the last talk of the session is by Edward Eaton, David Zhao, Chelsea Komlo, and Youssef Mokrani towards post-quantum key updatable public key encryption via supersingular isogenies. And Youssef, I suppose Youssef, you're going to give a talk.
Yeah, can you hear me / see the screen?
Yes.
Okay, so let's start. Today we'll be talking about post-quantum UPK scheme using supersingular isogenies. The motivation behind our paper is that a lot of online conversation can occur during months, if not years. And for those types of conversation, we require that the security scheme used is post-forward secure and post-compromise secure. Key updatable public key encryption, also known as UPK scheme, have been proposed to solve that issue. However, all current UPK scheme rely on discrete logarithm, which is not quantum secure. So the idea of a paper is to use supersingular isogeny, which are quantum secure, to cover that problem. A UPK scheme is simply a tuple of 6 algorithms. We have our key generation algorithm with the encryption and decryption. We have an algorithm to generate the update value and 2 algorithms to update the keys using that update value. From UPK schemes, we require 5 property correctness, obviously. We also want forward security, which means that obtaining the updated key should not give information on the original key. We want post-compromise security, which is the other direction. We also want asynchronicity, which means that any party involved in the scheme should be able to update the keys. And finally, we want key indistinguishability, which means that given a key, we should not be able to tell the number of updates on that key. To simulate all these properties, we created a security game that we call IND-CPA-U, which is just a modification on the classic IND-CPA game, but we allow the adversary to also update and corrupt the keys. So since we're working on supersingular isogenies, we attempted a UPK scheme on both SIDH and CSIDH. We started with on CSIDH, when we have the basic SIDH exchange between Alice and Bob. The naive update on Alice's key would simply to add the second isogeny and have that the new secret key is the composition of the 2 isogenies between the initial curve and the end curve. However, this is not forward secure because obtaining the composition of the isogenies would give most of the information on the original isogeny. So to solve this problem, we use an algorithm called KPT star, which is able, with given some information, to generate an independent isogeny between two given elliptic curves. So we can use that algorithm to simply modify the composition to get an independent elliptic curve between the same domain and image. However, there are two issues with that method. The first one we cannot solve is that KLPT star requires information that are part of Alice's secret key. So we lose asynchronicity. Also, after multiple updates, the degree of the isogeny becomes too large to be defined by the kernel. For the second problem, we can simply separate the isogeny into smaller isogenies, and then use linear algebra to do multiple SIDH exchanges. So this scheme respects correctness, forward secrecy, and post-compromise security. However, because of KLPT star, we don't have asynchronicity. And because of the chain, we don't have key indistinguishability, as the number of elements in that chain gives away the number of updates. On the other hand, for our CSIDH UPK scheme, we also started with the naive version, which have been where the secret key is just a vector of integers, and the public key is the group action represented by that vector. And the naive update would simply to generate a second vector, have the new secret key be the sum of the vectors, and the new public key be the action of that new vector on the public key. However, we don't have forward security if we just do that, simply because the new possible keys are always centered around the original key, which means that giving away the updated key would give information on the original key. Also, after multiple updates, the vector becomes too large for any sort of fast calculations. However, we can solve both those issues by an idea from the author of SciFish, which is to, instead of representing SK as a vector, we can represent it as a group element, as long as we know the group structure. For example, in CSIDH by round 12, we know that the group is cyclic. And because we represent it as a group element, both our issues are solved. And the SciFish paper describes a process to switch between the two representations. And because of that, our version of CSIDH UPK is IND CPAU if and only if CSIDH is IND CPA. So to conclude, the possible advancements we could do is first of all, for the SIDH version, we could obtain key indistinguishability if we find a way to get an upper bound on the number of chains in our isogeny. And for CSIDH, we always require to get group structure if we want to use multiple security parameters. There is a current exponential algorithm, but if it is too slow, since we are talking about post-quantum algorithms, as long as one person in the exchange has a quantum computer, they can just evaluate the group structure to get our exchange, even if the other parties don't have a quantum computer. So this concludes the talk.
Okay, thank you for the talk. So there are a few questions in the chat. So I suppose the first question is by Tanya, and this is related to the paper, to the boomerang attack paper, and also a subsequent question by Andreas. So let me read it here. Oh no, sorry. No, the first question is to Andre. Maybe I missed something, but 7/24 is the classical exponent for subset sum from Becker-Koronju. We go to 0.241. Can you comment on that?
Yeah. If you hear me, that's actually because so your algorithm in particular for from this paper is a dedicated algorithm for subset sum. But the algorithm I presented is not solving subset sum, it's solving the Folksdal problem, which is basically when you solve subset sum, you have the representation techniques, so you have further tools and further optimizations you can do. Maybe what would happen, for example, it would be more difficult, for example, in the worst case. I think the algorithms that you find in the paper could be applied in the worst case. But in the worst case, you can't apply the representation technique, and then then you don't have this 0.241. That's also actually the 7/24 has exactly nothing to do with the exponent from Becker-Koronju, even though it's practically the same value. Turns out also that the best exponent you have, the 2/7, is something that goes just little below Becker-Koronju. So you could use that to have a small quantum speedup over the classical algorithm. But it's above an improved algorithm with better representations that we did at Jabrek 2020. So it's also not not better than the dedicated classical methods.
Thank you. I think that's clear the question up. So the second question, sorry, is by Andreas. This requires quantum access to a secretly keyed primitive, right? So we talk about a Q2 setting attack. Can you predict the complexity if you are limited to Q1 PQ setting? And this question is to Paul.
Yes, I forgot to mention it here, but we need a Q2 setting. So we need quantum access to the primitive. And in Q1, you would need to get the queries and then put it in a QRAM. But then with the query cost alone, this makes some application not viable. For example, with the Favron Cepher++, the 2 to the 78 is already the data cost. So in the Q1 setting, we will not have any improvement.
Okay, thank you. And then the next question is by Crane Reinders to Jorge. How long is the chain of 2 isogenies approximately? And could the verifier use a higher degree modular polynomial, say 2 to the 8, to verify, say, 1 every 8 J invariants instead of every single one? Or is that slower than what you currently do?
Yes, so thank you for the question. So it depends regarding how long the chains are, depends on the delay that you want, obviously. But the delay that you can guarantee is based on the fastest known method of evaluation, right? So it's just evaluating 2 isogenies. So if you take for reference some benchmarkings on SIDH, for example, I think it would come down to about in the order of 1,000 steps per second of delay, something like that. Regarding verifying multiple steps at a time, I would expect it to be worse. Well, first of all, modular polynomials only exist for prime degrees. So you couldn't do like a modular polynomial of degree 2 to the 8, for example. You would need to get a little bit creative there, but even then, the verification ends up being logarithmic in the number of steps, but linear in the degree of the polynomial. So I think that the strategy would always be to split it into steps as small as possible.
So another question to Jorge by Watson Ladd. If I understand the time lock correctly, the path doesn't need to be secret, it's just long and big. Could commit and open work for it, or would the space be too much?
Yes, so it's, yeah, the path doesn't need to be secret. So the difference is it's not quite a time lock, it's a VDF. So the path is actually the input to the VDF. So every time you pick a different input, you end up doing a different path. I'm not sure what you mean by open work.
Oh, I mean that you'll store the whole path and you'll hash it. And then the verifier says, okay, well, you've committed to this whole path. Or you'll sort of Merkle tree and the verifier says, okay, you've committed to this whole path. Show me the 100th step and the 300th step and the 446th step. And you open those up, and now the probability of cheating is, if you do it sufficiently many times, is low.
Yes, so that's basically what the snark does. You end up including a proof, which as part of it has like a Merkle root of a hash tree for the J invariants. So you are able to verify each of the J invariants. but in order that is actually logarithmic in T. But it's basically what the snark takes care of.
I think we're, maybe I'll ask a few more questions. First question again, so, to Jorge. In terms of security, how does this compare to the isogeny-based PDF? Of course, there's a pairing evaluation at the end, which excludes them from being post-quantum, but do you have all the other issues of trusted setup and stuff like that, or is it different otherwise?
Right. So yeah, we also we do not need the trusted setup, and we do get post-quantum security. So that's all. Both of them are consequences of the fact that we're using like different isogenies each time. So for instance, for the BDF by DFL, the problem is you just have to compute images of different points, but always under the same isogeny, right? So if you compute a shortcut once, you broke it for all inputs. So that's why it's post-quantum. Sorry, that's why it's not post-quantum, and that's why it requires the trusted setup so that you cannot compute the shortcut. In our case, even if you compute a shortcut, as long as you cannot compute it faster than time t, it doesn't break anything.
Okay, thanks. Then to Charlotte. So is there any direct countermeasure to the adaptive attack? So there, of course you can do Fujisaki Okamoto, but is there any easier, more direct countermeasures? Yeah.
Not that I'm aware of at the moment. We suggest using Fujisaki Okamoto to get CCA2 security, but I can't really think of something that would prevent, maybe not using our points that we suggest for the adaptive attack, but I'm sure there is a way to evade some different kind of checks if there is something that would detect our kind of points.
So is there some Genius 2 or KSIDH or something like that, or I don't know if that's something that obviously fails or obviously works, just is very inefficient?
Sorry, you cut off for me. Can you?
Okay, sorry. So there are countermeasures for SIDH which are very inefficient, like KSIDH or something like that. Would that work in the Genius 2 case as well?
Yes, I think any type of variant can be, like specifically KSIDH should be able to be generalized as well. But as we've seen also in the KSIDH case, there are similar kind of GPST style attacks on KSIDH or the Zhao-Orbanik scheme, for example. So even though we haven't tried generalizing these, I believe it should be possible to also derive malformed points which would find the keys in these specific variants.
Okay, thank you. And since we're nowhere, I have one final question to Youssef regarding the UPT scheme. So you have various security properties, and so the SIDH construction doesn't satisfy all of them. For practical use, which security properties would you say are more important? So post-compromise and forward security are more important than asynchronicity? That's what you're, or?
Well, yes, because if we don't have post-compromise or forward secrecy, just the entire scheme breaks. Asynchronicity can still be used. It's not as, it can still be used, but we always need for every party to connect at some point for the update to work. But it can still work. But if we don't have forward secrecy or post-compromise security, it's just, the update is just worthless.
But you can make do without asynchronicity in practice.
Yes, it's just not as fast.
Okay. So if there are no more questions, I think we've gone way into the break now, but thanks for all the speakers of the session, and I think we can conclude